Hi guys, welcome to the next section, Utility Classes. Now we move on to the first video of this section that deals with conversion and safely signalizing function. Let's start with converting between different time units using STD ratio. Let's look at the entire code first. Here we will define a little game that prompts the user to enter a specific word. The time that the user needs to type this word into the keyboard is measured and displayed in multiple time units. At first, we need to include all the necessary headers. For reasons of comfort, we declare that we have used the STD namespace by default. The chrono duration as a type for time durations usually refers to multiples or fractions of seconds. All the STL time duration units refer to integer typed duration specializations. We are going to specialize on double. In the video after this one, we will concentrate more on the existing time unit definitions that are already built into the STL. 1 millisecond is a fraction of a second, so we will define this unit by referring to seconds. The ratio multiplied template parameter applies the STL predefined millifactor to seconds period, which gives us the fraction we want. The ratio multiplied template is basically a meta-programming function for multiplying ratios. It's the same thing with microseconds. While a millisecond is a millifraction of a second, a microsecond is a microfraction of a second. As you can see, ratio template parameter applies STD predefined macrofactor to seconds period, which gives us the fraction we want. Now we are going to implement a function which reads a string from user input and measures how long it took the user to type the input. It takes no arguments and returns us the user input string as well as the elapsed time, bundled in a pair. We need to take the time from the beginning of the period during which user input occurs and after it. Taking a time looks like this. The actual capturing of user input takes place now. If we are not successful, we just return a default initialized tuple. The caller will see that he got an empty input string. In the case of success, we will continue by taking another time snapshot. Then we will return the input string and the difference between both time points. Note that both are absolute time points, but by calculating the difference, we will get a duration. Let's implement the actual program now. We loop until the user enters the input string correctly. In every loop step, we will ask the user to please enter the string C++17, and then call our getInput function. Then we will check the input. If the input is empty, we will interpret this as a request to exit the whole program. If the user correctly types C++17, we will express our congratulations and then print the time the user needed to type the word correctly. The diffCount method returns the number of seconds as a floating point number. If we had used the original STL seconds duration type, then we would have got a rounded integer value, not a fraction. By feeding the milliseconds or microseconds constructor with our diff variable before calling count, we will get the same value transformed to a different unit. If the user has a typo in the input, we will let him try again using this line of code. Now let's compile and run the program. We will compile our code using this command. It will give us this output. At first, we will input a typo. The program will repeatedly ask for the correct input word. After that, we will type the word correctly. It displays how long it took us to type it in 3 different time units. First, it will show in seconds, then in milliseconds, and then in microseconds. So as you can see, we have successfully obtained the output. We will now see converting between absolute and relative times with STD chrono. Now let's look at the entire code. We are going to save the current time and print it. Additionally, our program will add different offsets to the saved time point and print the resulting time points too. The typical include lines come first. Then we will declare that we use the STD namespace by default. We are going to print absolute time points. These will come along in the form of the chrono time point type template, so we will just overload the output stream operator for it. There are different ways to print the date and/or time part of a time point. We will just use the %C standard formatting. We would, of course, also print only the time, only the date, only the year, or whatever comes to our mind. All the conversations between the different types before we can finally apply put time look a bit clunky, but we are only doing this once. There are already STL type definitions for seconds, minutes, hours, and so on. We will add the days type now. This is easy. We just have to specialize the chrono duration template by referring to hours and multiply with 24 because a full day has 24 hours. In order to be able to express a duration in multiples of days in the most elegant way, we can define our own day's literal operator using these lines of code. Now we can define 3 days to construct a value that represents 3 days. In the actual program, we will take a time snapshot, which we will simply print afterwards. This is very easy and comfortable because we already implemented the right operator overload for this. Having saved the current time in the now variable, we can add arbitrary durations to it and print those too. Let's add 12 hours to the current time and print what time we will have in 12 hours using this line of code. By declaring that we use the chronoliterals namespace by default, we will unlock all the existing duration literals for hours, seconds, and so on. This way we can elegantly print what time it was 12 hours and 15 minutes ago or 7 days ago. Let's compile and run the program to yield the result. We will go to the terminal and run this command. So you can see our program is compiled. Because we use %c as the format string for time formatting, we get a pretty complete description in a specific format. By playing around with different format strings, we can get it in any format we like. Note that the time format is not 12 hours AM or PM, but 24 hours because the app is run on a European system. Next, we will see safely signalizing failure with STD optional. Now we will implement a program that reads integers from the user and sums them up. This is our entire code. Because the user can always input random things instead of numbers, we will see how optional can improve our error handling. First, we will include all the needed headers and declare that we use the standard namespace. Let's define an integer type, which maybe contains a value. The std optional type does exactly that. By wrapping any type into optional, we give it an additional possible state, which reflects that it currently has no value. By having defined an optional integer type, we will express that a function that usually returns an integer can also possibly fail. If we take an integer from user input, this can possibly fail because the user might not always enter an integer even though we asked him to do so. So returning an optional integer is perfect in this case. If reading an integer succeeds, we feed it into the optional int constructor. Otherwise, we return a default constructed optional, which signals failure or emptiness. We can do more than returning integers from functions that can possibly fail. What if we calculate the sum of 2 optional integers? This can only lead to a real numeric sum if both the operands contain an actual value. In any other case, we return an empty optional variable. This function needs a little more explanation. By implicitly transforming the optional int variables a and b to Boolean expressions, that is exclamation A and B, we get to know whether they contain actual values. If they do, we can access them like pointers or iterators by simply dereferencing them with *A and *B. Now we will add a normal integer to an optional integer that follows the same logic. On this line, we will add normal integer to optional integer. Let's now define a program that does something with optional integers. We will first let the user enter 2 numbers. Then we will add those input numbers and additionally add the value 10 to their sum. Since a and b are optional integers, sum will also be an optional integer type variable. If a and b do not contain a value, then sum cannot possibly contain a value either. The nice thing about our optional integers now is that we do not need to explicitly check a and b. What happens when we sum up empty optionals is perfectly sane and defined behavior because we defined operator plus in a safe way for those types. This way we can arbitrarily add many possible empty optional integers. We'll only need to check the resulting optional value. If it contains a value, then we can safely access and print it. If the user enters something non-numeric, we error it out. That's it. Let's compile and run the program. Open the terminal and run this command. Let's execute the program. It will ask us to enter 2 integers. We will get the output like this. We will now run the program again and enter something non-numeric. It yields the error message.